So let's see, what do we got? Number 2, you needed to repeat the previous question if the force was above the horizontal instead of below the horizontal. So all of the answers are decrease. I agree with that? Yes. All right, are we good? All right. Number 4, in 3 experiments, you got blah, 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 blah. So let's see. So for A, you had to rank the magnitude of fx. So you had to rank them from what? From greatest to least. So that one should be F1, F2, F3. I guess I could write it down. And then finally, B is the same. That's the same. Any problems on that one?
Wait, is B the same as A?
No. You're ranking them. They're all the same. So it's...
Oh, okay, yeah. I got it.
Good? Gotcha. That was unclear. All right, everybody good? Okay. All right, number 5, if you press an apple crate against a wall so hard that it can't slide down the wall. So here's your wall, here's your crate, here's the force of you. So while we're at it, what are the other 3 forces? Gravity, normal force. Point for me, which way? And friction, how should I label it? F for force, what kind of?
Static.
Friction, static. Max? No, that's just however much it's exerting, right? Okay. All right. So that's what your drawing should look like. And then you had to answer the questions. You had to give the direction of the different forces. So here are the answers. A is up. B is, I put out, meaning away from the wall, right? C, what is C saying? Oh, if you increase or push, what happens to each of the things? So C, it stays the same. And then D and E are both increase. Cool? Problems, you guys? You guys make me nervous when you don't ask questions. All right. All right, number 6. So this was the one where you had to make the graph, right? Yeah, okay. All right, so here's the drawing. Let me embiggen this a little bit. Hopefully that worked. No, it didn't. There we go. Okay, so let's see. It says in the figure right, a block of mass m is held stationary on a ramp by a frictional force on it from the ramp. A force F directed up the ramp is then applied to the block and gradually increased in magnitude from 0. During the increase, what happens to the direction and magnitude of the frictional force on the block? Make a graph of the frictional force as a function of F. So our graph is going to look like this. Here's the force that we're applying. Here's our force of friction static. Okay? So, here's our block. Right? So, if our applied force is 0, the problem is telling you that it's stationary, right? Okay, so automatically I know that there's this parallel component of gravity pulling the block down the ramp, correct? Does that make sense? Now, if there's no applied force, then what has to be true about that force of static friction? Does it have to equal the max? It's got to equal this parallel component, right? If it's being held at rest, then I know my net force has got to be 0, right? In fact, that's going to be true for all of this, right? No matter what F is, since it's stationary, my net force is 0. So with no applied force, in other words, if F is 0, then my force of static friction has got to be the same as Fg parallel, right? So that tells me my y-intercept. So there's one data point. Let me pause there. Does that make sense? All right, now, here's F. So if F gets bigger, keeping in mind that my net force needs to stay 0, what's going to happen to the force of static friction? It's going to get smaller, right? So it's this, right? Okay? So at what point, as my F gets bigger, eventually you're not going to need static friction anymore, right? So what value of F means that there's no static friction? If this is FG parallel, then my static friction is 0. So remember. So there's another coordinate, right? Does that make sense? All right, now, here's the weird part. What if F gets bigger still? Like, maybe this would be easier if we put some numbers in. Here, let's do this. Let's say this FG parallel is 10 newtons, right? Good. So right now, my applied force is 10 newtons, right? All right. What would happen if my applied force was, say, 11 newtons? Would it? Would it start moving up? Oh, right. Friction still doesn't want it to move. Friction doesn't want the block to move down the ramp or up the ramp. Right? So right now, my applied force is winning, but static friction is like, whoa, dude, I've got maximum amount of force at my disposal, right? So let's suppose that the maximum force of friction is 20. How much force do I need to get it moving? Up the ramp. 30, right? Okay. So it's not until this force is FG parallel plus FFS max, that's when it's going to start moving, right? Oh, sorry, I put perpendicular instead of parallel. Thank you, Nathan. Does that make sense? All right. And what's going to happen is, at that point, my static friction can go this way with a force of up to the maximum, right? So, let me see, I gotta carve out some room on my board here. Oh, darn it. So, let's see. So what we just decided was that when this force is Fg parallel plus FFS max, then my force of static friction is going to be negative FFS max, right? Because now it's pulling down the ramp. Follow or no? All right. Basically, though, what you get is you just get a nice straight line that goes like that. And after this force, after you exceed your maximum friction, then it moves, and then it's a different problem. Make sense? Very abstract problem, right? No numbers. But important. What do you got?
Is that like kind of
Yeah, totally. Totally AP type of question. I was going to say that. All right. Are we good? All right. Number 7 is similar, except in 7, we're going to push the box down the ramp, right? All right. So any questions on 6 before I go on to 7? Do you guys want me to, why don't we do this? I showed you how to do 6. Why don't you guys try 7, and then let's talk about it again on like Thursday. Does that sound good? Now that you've seen how this works? Fair? Cool. Remind me if I forget, okay? There's a good chance of that. All right, so that's 6. All right, 7 is similar. Oops. All right, number 8, I like this one too. All right, so we've got the slab and this block, and we're going to pull the slab with a force of 100 newtons. All right. Now, it tells us that both of our blocks are 10 kilograms, right? 10 kilogram slab, 10 kilogram block. So 10 kilograms, 10 kilograms. So everything in the problem is 10 kilograms. The problem is, let's see, the floor is frictionless. So down here, there's no friction, but there might be friction between the block and the slab. Okay? So, question A says, considering that possibility, the fact that it might be frictionless or it might not, what's the possible range of values for the magnitude of the slab's acceleration and the block's acceleration? Okay, so A, let's see. What would happen, what would the slab and block do if there was zero friction between the block and the slab? Sure, what do you got out? The slab would move, but the block wouldn't, right? So no friction. You know what? These are, I'm going to kind of do A and B at the same time. Let's see. So if there's no friction, then here's my slab. You're going to have 100 newtons on it. Would there be any other forces that are going to affect its motion? No. So the acceleration would be net force over mass. We've got 100 newtons pulling this thing. It's 10 kilograms. So the acceleration you would get is 10 meters per second squared, right? Good? And in those same circumstances, what would the block do? It would just stay at rest, right? If there's no friction, then the slab is going to move and the block is going to stay at rest. So the acceleration is zero, right? That's like when I had the track up here with the cart on it, right? You can pull the track and the cart doesn't move, right? Good or no? Okay, so that's if there's no friction. Now, dang it, what happens? I always forget to set that. Control K. Arg. Control K. There we go. All right? Yes. Okay. So, all right. Now, there could be some friction, but just a little bit, so that the block moves a little bit, but not a lot. The maximum would be if there's enough friction that the block and the slab move together, right? Is it possible that there's so much friction that the block goes faster than the slab? No, that doesn't make sense, right? So if there's enough friction, well, if there's enough friction, they're going to move together, right? So I shouldn't have, that looks like a net, sorry. I was trying to save time.
I thought that's what it was.
No, it was supposed to be the sum of enough. All right, so if there's enough friction, they're going to move together. So that 100 newtons is now moving, what, 20 kilograms. And so now the acceleration is, 100 over 20 is 5 meters a second squared, right? So those are sort of our ranges. So the slab is going to have an acceleration somewhere between 10 and 5. And the block is going to have an acceleration somewhere between 0 and 5. That's it. Those are the only possibilities. Yes?
If the block moves with the slab, is it considered static friction between them?
This would be static friction.
Yeah.
Now, you might get one of these situations where the block moves forward a little bit, but just not as fast. Then it's kinetic.
But if it's static, it's
Right.
okay.
Right. Make sense, you guys, or no? This would be worth, like, if you, because you guys have all this extra time, because I'm barely giving you any problems. Sorry. It would be worth trying some different coefficients of friction. Like, see what happens if your coefficient of static friction is 0.2 and your coefficient of kinetic friction is 0.1. See what happens. Do, 0.3 and 0.2 or, whatever. Try some different ones and see what happens. There are situations where the block and the slab both move, but not with the same acceleration. And that's worth investigating. Okay? In fact, that would be actually a really good, free response question. So, all right, everybody good? All right. So, that was it for the concept-y stuff, I think, wasn't it? Oh, 13. These problems take so long to go over. Let's see, what was 13? You just had to say increase, decrease, etc. So A, B, and C are all increase, and D and E are decrease. Was that somebody say crap? Want me to go over that?
I didn't get this.
Others want me to go over it?
Oh,
C? Okay. Well, I wonder if I made a mistake. That is possible. Let's see. I finally just found where they save the answers to these ones. So some of these I haven't checked my answers, so let's see if there's a mistake. All right, so we got a box on a ramp that's at an angle of theta to the horizontal. Ramp, theta, box. Oh. Okay, cool. Let's see. Which of do the following values increase, decrease, or remain the same? As what? Oh, as the angle increases. Okay. So, as your angle increases, yeah, clearly your component of gravity along the ramp is going to increase, right? As it gets steeper, gravity pulls down with more force. Your static frictional force, as long as it doesn't move, yep, before the box slips, right? If the ramp is getting steeper, that means you've got more force pulling it down, so you have to have more static friction working against its motion down the ramp, right? Good. So here, let's just do this. This is Fg sine theta. Your force of static friction has got to equal, what's up? Oops, I didn't do that. All right, so that's all of our forces, right? Parallel component, perpendicular component. Your normal force has to equal your perpendicular component. And if it's not moving, your friction has to equal your parallel component, right? Okay? So, let's see. C, the component of gravitational force on the box perpendicular to the ramp. As your angle gets, yeah, that should totally decrease. That's the point. Oh, you know what's the worst is I have it right on my paper.
We'll give it anyway.
I'll give you the points anyway. I'll give you the point anyway. Stand by my promise. So that was 6.1, number 13. I think is that 2 or 3? 1 point? 1 point? That's 2. I think that's 2. Okay. Yep, my bad. All right, so are we good? So C was supposed to be decrease. Oh, that's frustrating. It's the second time I've done that. Okay, are we good? All right. All right, problems. What do we got? So I already did the ones that are up there from 6.1a. They're on the interwebs. So take a look at those, and then if you need more help, come see me before after school. So I'm looking at 6.1b now. 25 has a lot of votes, and 60 and 84 have a lot of votes. 25? All right. By people being vocal, we'll start there. Oh no, too far, too far. Oh. All right. 25, 25, 25. Oh, what one is this? Show in class 33. Is 33 on that list?
We didn't know.
Oh, did I not assign?
33 is not a sign.
Oh, great. Okay, cool. We might have to do that one as an example then. All right. What am I doing? I'm sorry. I totally lost my train of thought. 25, 25, 25. Okay, so here we go. All right, so block B in the figure at the left weighs, so the force of gravity on B is 711 newtons. The coefficient of static friction between the block and the table is 0.25. The coefficient of static friction is 0.25 newtons. Let's see, the angle theta over here is 30 degrees. This is just me writing out my givens. I start every single problem this way. Assume that the chord between B and the knot is horizontal. I don't know what that little arrow is supposed to... All right, let's see. We got to find the maximum mass of block A for which the system will be stationary. So, thoughts about where to start? Static friction max, right? So, if we look at block B, here's block B. we know that the force of gravity on block B is 711 newtons. Since the force from the knot is horizontal, automatically I know that my normal force must be positive 711, right? All right. Here's the force from the tension in the rope. What's going to prevent it from sliding if it doesn't move? Static friction. Well, so we should find the maximum value, right? So our maximum value is going to be our coefficient times our normal force. So 0.25 times 711 gives us 177.75. Seriously. So max 177.75 newtons. All right, so everybody get up to there. All right, that means that as long as our tension is that number or less, we're good, right? So let's assume worst case scenario and assume that the tension is also 177.75 newtons, right?
Yeah.
Good?
Wouldn't it have to be that? Because it's a completely horizontal. So this is,
As opposed to what? I guess I'm not sure I see what you're asking.
actually, wait, never mind. I was just confused for a second.
So the idea is the heavier this mass is,
Yeah.
the more tension there's going to be, right? Is everybody good? Okay. So, I guess the next thing we want to do is probably look at the knot. What should that net force of that knot be? It's got to be 0, right? Otherwise the knot would be moving in one direction or another, right? Okay. So, let's take a look at that. Let me clear this up a little bit. Oh no! Why can't you be more like your brother? All right. Okay, so here's the knot. All right, so here's what I know. I know that the tension pulling this way on the knot is 177.75 newtons, right? Now, there's this rope pulling up that way, right? Okay, well, that's got, let's call this, we need to give this a name. We can't call it tension because we've already used that. Let's call it, I don't know, let's call it F1. How about? Oh, T2, that would work too. Okay. FT2, I'm cool with that. Call this FT1. FT1. All right, so that FT2 has two components. It's pulling horizontally, and it's pulling vertically, right? What does the horizontal bit have to be? It's got to be 177.5, right? Because that knot's not moving. So this has got to be 177.75 newtons. And since I know this angle is 30 degrees, I can find my vertical bit, right? So what I'm looking at is this. Here's my force of tension 2. Here's my angle, 30 degrees. We know that the force of tension 2 in the x direction is 177.75 newtons. So we can find our F of tension 2 in the y direction just by using which trig function would help us there. Sine would get us the hypotenuse. Tangent will get us the adjacent side. So if you find that, you get 102.62. Right? Well, if my net force is 0, then that means the force of gravity, well, technically it's the force of tension 3, right? But that's going to equal the force of gravity on the block, right? So that's got to be 102.62, which means that I'm out of room, but so here's my block. Force of tension 3 is 102.62. That means my force of gravity on that block is also 102.62 newtons. So divide by 9.8 to get your mass. And it gives you pretty close to 10 kilograms. It's a little bit more, but with sig figs, you round it down to 10. Does that make sense, you guys?
Yep.
That's really common where you do this, where you split your forces up into components like that. It's a very common trick. All right, problems with 25? All right, I mean the following in a non-snarky way. What was hard about that? Like, where did you get tangled up? I don't mean like, what was hard about that? I mean, okay, a lot of pieces. Not attached to the, oh, this up here? Gotcha. That's probably true, yes. You could still solve it if it wasn't for the horizontal. It's just a lot harder. All right. So, but does the process I went through make sense? Yeah. I mean, honestly, I kind of followed my nose here. I said, well, we're worried about block B slipping, so I started with block B, right? And you guys told me, you said, oh, well, find your maximum friction. And so that was where we started, right? And then it's like, well, where do you go to next? Well, following the path, this knot is the next thing that we need to worry about, you know? So, I don't know. The more of these problems you do, the more you learn to, you know, sort of figure out these little tricks and stuff. So you'll get there. We good? All right. I think we have time for one more. What's next? I got 84 and 60. It looks like. Who wants 84? 1, 2, 3, 4, 5, 6, 7 84s. Who likes 60? 1, 2, 3, 4, 5. I think 84 just one. What's that? Oh, the box of ants, uncles? All right, so what did I just say, 84? Nice try. Did I really assign 84?
Yeah, that's why I'm sure 84 is pretty much graph.
Does it say that on there?
Yes, graph.decimals.com.
Yeah, you'll want to use
That's a little convoluted.
All right, hold on.
The point? I don't think they'll still ask you to like go on.
I can't believe I didn't delete this.
There's 60.
Do you know what? No, we want to do this. I assigned to this on purpose. I'm not super worried about the actual drawing of this graph, but the process of getting to the equation that you graph is important. Okay? So I did assign this on purpose. All right? And in particular, I want to point out something about part B, and then we'll talk about C and D. All right, so here we go. So here, let me lock this so that it doesn't move around again. Control K. All right, so here we go. Thank you. I'm sorry, you guys. Sometimes I forget what the problems are because I'm trying to work ahead so that I'm not constantly scrambling, and now I'm far enough ahead that I haven't looked at these now in a week or two. All right, so let's see, 84. In the figure, F is applied to a crate of mass M on a floor where the coefficient of static friction between the crate and the floor is mu s. The angle of theta is 0 degrees, but it's gradually increased so the force vector rotates clockwise. In other words, it's getting farther and farther below the horizontal. During the rotation, the magnitude of F is continually adjusted. Oh, so F is changing. So that the crate is always on the verge of sliding. Okay? So, let's pick an arbitrary theta and draw what the free body diagram would look like. All right? So, I guess we're using red. So here we go. The block has a mass M, right? Okay? That force, F, is going to have a horizontal bit and a vertical bit, right? So here's the horizontal bit. That's just going to be F times the cosine of whatever my angle is. And there's going to be a vertical bit, which is just going to be F times the sine of the angle. Is everybody good with that? All right, now, gravity's always going to be there. Oops, that's an FG. I guess we should clean it up. Dang it. FG. What's wrong?
You like that.
Oh, did you? Oh, I shouldn't have erased it. All right, here's my normal force. It's got to be equal to these two guys added up, right? So how did I write it here? I wrote that as mg plus F sine theta. That's your normal force, right? Okay? And then it says that it's always adjusted so the F is just putting it on the verge of sliding. So this force over here is my F,
Max.
my static friction max, right?
Max.
Does that make sense? Because otherwise it wouldn't be on the verge of sliding, right? Well, that maximum friction is hard. Oh, I hate you. It only does this hour. There it goes. Okay. So this should be my coefficient times my normal force. That's mu s times mg plus f sine theta, right? So is everybody good? Notice I was able to put together my free body diagram even though we don't know any numbers, right? That says max. Okay. So what are we trying to do? We want to plot a ratio of F over mg. So how do I want to say this without telling you what I want you to say? What information is going to give me a useful equation, do you think? Like, I'm going to start with an equation and then rearrange it and see if I can come up with an equation for F over mg. So where do I want to start? Let's give everybody a second to think. Okay, sure. What are you thinking, Jake?
Set the x force equal to the force of friction.
Good. Yeah. Yeah, because the x component in this actually has, it sort of deals with everything, right? Okay. This one doesn't really give us that much information, I guess. All right, so here we go. Let's scroll down. We are totally going to run out of time, but let's see how far we can get. So here we go. So if we set fx equal to ffs max, you get f cosine theta equals mu s times mg plus f sine theta. Good? All right, so do we know the coefficient of friction? Did it tell us? What is that? Oh, for mu s equals 0.7. Okay. All right. Well, let's not even worry about it. We'll plug it in later on. Okay. So I want to somehow come up with an equation for F over mg. So thoughts about my algebra. What would be a good thing to do next? That what by itself? Right. I agree with you, but yeah. We got to distribute this mu s. You're totally right, Mickey, but I was looking for a little more guidance. All right, what if we move all of our f's to one side? Okay, so let's subtract. So we've got f cosine theta minus mu s f sine theta equals what? Mu s mg. Aha, so now I can factor out an f. Oops. Right? Oops, and this is equals. Does that look right?
Yes.
So now if I divide both sides by mu s and by f, I get what I was looking for, right? Or am I looking for f over mg or mg over f? F over mg. Okay, so I want to divide both sides by mg. All right, so I'm going to divide both sides by mg and divide both sides by this mess. All right, so being able to graph this, there's no way you'd be able to graph this on your own. Okay, but you could certainly do it with the graphing calculator. That's what I was asking you to do, and I'll leave you guys to do that on your own. All right, we only got 1 minute here. Is everybody okay with how I got here? All right, now, here, let me do this. Oops. Hang on, don't go away. All right, check it out. Question B, determine the angle at which the ratio approaches an infinite value. When does a ratio go to infinity? if the bottom is 0. So to do part B, you just set the bottom equal to 0, which is actually not that bad. You get cosine of theta minus mu s sine theta equals 0, so you get this. Right? So if you divide both sides by cosine, it gives you tangent, right? So you get tangent of theta equals 1 over mu s. We'll just do inverse tangent. Right, that is a common trick, you guys, where you've got the sine and this cosine, and you need to find the angle. See if you can take your sine and your cosine and convert it into a tangent. All right, that was why I wanted you to do this problem. Real quick. Well, all right. I'll see you tomorrow.